体出话头。
Hello, 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 hello. 不能够可能两个。啊？make sense 咩？
如果他的头是电才
哦，以前的话，我们用这个 connect，它也是只能够接一个，你一个可以讲话，一个不能，一个讲话会沙沙沙。嗯，它不是应该只要接到 frequency 就可以接了？哦，哦，你的意思是讲用不同 frequency 接到？
方面嗯，对。
Okay, let's start. So first hour we will have a lecture, and then second hour we have sharing section on Edmund. Maybe Edmund's here. So hopefully Edmund can share some his story with mathematics. Okay, how he view maths, right? And then hopefully he can tell you what algebraic geometry can do. Okay. Yeah, and maybe we will have some I'll say non math related story, that fun story that when we do collaboration, right? And how collaboration can bring you work and new result. And then yeah, so maths is not just about calculating or memorizing formula theorems, right? Okay, so you really need to appreciate it, okay, to apply it in a meaningful way. Okay, right. So before we start, okay, so I'll try and keep awake for this hour, next hour, sharing. So for before we start, yesterday we got a few problem here. So our first problem is yesterday Hao Tian, right? Hao Tian. So actually, we are not referring to the inverse image of C is smooth. Actually, it's that C bar is smooth. Okay, that C tilde, sorry, that we kind of call it a lift. Okay, and so remember that this C tilde here is the Zariski closure, okay, of the pre-image of C taking away the origin. Okay, so yesterday I kind of used limit concept to tell you, right, Eric, correct or not? Yeah. But you really you can see that continuity using the Zariski topology sense. Okay, so using the Zariski topology to talk about continuity, that should be fine. And then second follow-up question by Hao Tian is, can I blow this thing up or not? Only then I realized that y equal to absolute x seems like not polynomial. I mean, anyway, I tried to draw this picture out, but I don't know whether it makes sense or not. But just realize that absolute x is not a polynomial. I don't think it's helpful here.
It's too polynomial.
It's too okay, piecewise.
So it's not irreducible.
Yeah, not irreducible. Okay. And then one more thing is okay. In the end of the class, I make a false claim, right? Anyone remember the false claim? The last claim I left yesterday. The false claim.
Oh, the whole space.
Yes. Okay.
You say
It's not irreducible, but last time we classified, for example, the diversity topology for A1, right? A1 is one of the irreducible, right? Okay. So what's the problem here? What's the contradiction yesterday? What do we start with? We start with a hypersurface, right? So think about this hypersurface here, where F is irreducible. Can F be zero whole number? F irreducible. Huh? 变什么 factor 出来？ Zero is irreducible. Why? The integral of the irreducible differential already throw away the zero. Sorry? S squared 减一等于零。Okay, so there's two things you need to recognize here. So there's few things you need to recognize here. So what does it mean by it is a non-zero polynomial? What it is, it means by a zero polynomial. What does it mean by when the function equals to zero? Do you recognize that these are different things? So for the three equality here, right? Three line equality here, this is identically zero. Okay. So meaning no matter what you put into is zero. But if you talk about a function or a polynomial that's non-zero, you can talk about where it is zero. Okay. For just now, what's the defining function polynomial for whole space? Is the zero polynomial. But if f has to be irreducible, f first cannot be zero. Okay, that's the definition for irreducible element. Okay, it also makes sense, right? It also makes sense, right? Because we are looking at a hypersurface of a affine space. Okay, we are not looking at okay. Okay. Happy? Eric, happy or not? Happy 啊？这样敷衍呢？
I'm so happy.
Okay. Okay, so if you have any question, please just let us know. Try to solve it. Okay. All right. So today we will continue to define a dimension, smooth point, singular point for affine varieties in general. Okay, yesterday we do it for hypersurface. Okay. So you should keep in mind that what we do for hypersurface, and then see how it generalizes to general affine varieties here. Okay, so let's do dimension and smooth singular. How? Varieties. Okay, so what the first thing we do yesterday? Given you the defining polynomial, what do you do? Lydia, what do you do yesterday? the keyword start with P. Partial. Huh? Partial derivative. Okay. So let's say we take any function, okay, polynomial, and look at a specific point. We will define something called the linear part. Okay, the linear part of f. Okay, and this e here is defined by the following. So instead of write f prime, they write f1 here. Maybe they can generalize later. But this is the book notation. Basically, this is just sum of partial derivative of f with respect to each coordinate at p prime x1 minus a. Okay, and then you sum all the direction. Yeah. Okay. Then how do we define tangent space in general now? So this is the if this f is irreducible, and then you look at the zero set of this linear part here, this is exactly the tangent space for your hypersurface. Okay. But now we're gonna define a tangent space affine variety. So in affine variety, what's the difference between affine variety and hypersurface? What's the difference? You could have more f, right? Okay, you could have more f inside your defining ID, right? Okay, so in this case, what we're gonna do is we will define it by the intersection. Okay, intersection of all the f in IV, okay, of the zero set of this linear part. Okay, so we'll look at the intersection for this linear part of f. Okay, so this is a subset of A. So similarly, you could show that this is an affine subspace of AN, okay, containing P, similar to what we have done last time. So if V is a hypersurface, then there's only one F. So there's only one PF, P1, P here. Make sense? Okay, if you have more F, you take the intersection. So far, okay? Okay. So remember that this is a subspace, okay, subspace of ANK, right? So we can view AN as a vector space. Okay, so this is just a vector subspace. So in this case here, we're gonna define next things. So for an affine variety, we could define its dimension. The dimension of B. Okay, so how are we gonna define this dimension then? It is just the minimum of all the dimension of TPV for all P. Okay, so for each P, you look at this intersection, it's a vector subspace, count the dimension, and look for the minimum one. Okay, across all the point in your variety. So far, okay? Okay. So from this definition, right? Minimum definition here. So first remark, what can you see here? So if for every P in V, your dimension of tangent space must be greater or equal to the dimension of V. Okay, make sense? Okay, and later we're going to show you that, maybe put a claim here. Okay, I'm going to show you that. In fact, dimension V is always equals to dimension TPV. Okay, so there's a very vague word here for generic point P in V. And later you will know why is it a generic point here. Okay, so how to think about this? Remember the adjective of open and dense. Okay, open and dense. So when do we see open and dense idea? When do we see open and dense? One place I remember is on the rational function, dom f. Okay, could be defined on a quite large set, right? So dense means after you taking a closure, actually it's the whole variety. Okay, so generic point here is a similar idea. Okay, if you don't pick some very big, like very weird point, you will always get this equality. But later we will see what kind of point is this. Okay, so before doing that, we need a proposition. So if we look at this function here, so going from the affine variety to n. Okay, so what does this do? Basically, you just take a point, send it to the tangent space, the dimension of tangent space at this point. And this function is upper semi-continuous. Okay, I will define what it means. So first time seeing this. So what's this upper semi-continuous saying here? So this is continuity at the Zariski topology. Okay, it means that for every r in the natural number, okay, this particular set here, we call it a SRV, okay, which is defined by all the points in V such that the dimension of tangent space at this point is greater or equals to r. Okay? So basically, we collect all the points such that its dimension of tangent space is greater or equal to some natural number here. And then this set is closed. Okay. So far, okay. Okay, basically, this content is to show that this set here is closed.逗号在哪里？那个逗号，什么要逗号啊？要逗號嘛，你們？誒，OK, I mean from 我們 OK from 我們的，我記得我們有一次 like 被 edit 那個叫什麼呀 editor like 如果每次好像我們把它放在中間的話，要我們放一個逗號不是 ？But like 如果你放連下去的話就不用了。But yeah, but 啊什麼？呀，我沒有 centralize 它，但是就 OK 有一個 benefit of doubt 就是 like 我告訴你我的 equation 結束了啦，就這樣，我沒有顯露什麼東西，我是這樣 view 它了。But anyway 你不要多就不要多了。But yeah. Okay. All right. So, hey, this yeah, this is closed, so it means that it has to be a zero set or something, right? Okay, but maybe you can see that this defining property here is a how's that? Half open, half open. Okay, but obviously this is not a polynomial, but so Can you imagine what kind of zero set is satisfied? You need to stay inside this. You want to look at TPV, right? You have to stay inside TPV is a zero set property. Okay. Okay. So let's write down what we have here. So let's see how many function we need. Okay, to define this variety here. Well, I think we know from Hilbert basis theorem, if I'm not wrong. Okay, so we just need finitely many of them. Okay, from the Noetherian property. Then the claim is if you look at all the other f in the IV, right? Okay, all the f in IV. Let me see. Is this correct or not? If you look at all the f in IV, I feel like this line is not correct. So let me write down this line correct. Things very weird. Oh, wait, why do I write I? Let me think for a while. Okay, I think what I want is if I calculate the linear part of this f here, linear part of this f is this, right? I should be able to write it as a linear combination of the linear part of GI. Does it make sense? Make sense? Because f is a linear combination of GI, and then if you partial derivative, take partial derivative from f, those partial derivatives should apply on G. Make sense? Okay. Okay. So instead of looking at all the intersection of the uh, linear part of all the f, right? So basically, you just reduce it to taking intersection of all the linear part of GI. Okay, this thing living. Okay. Well, in this case, how do you count the dimension? How do you count the dimension? How do you count this dimension then? Okay, at most what? This is the at most what? N, right? At most n. Okay. Could it be less than n or not? Okay, how is it less than n? Is that this vector space here is the intersection of these? Right. Okay. Intersection of these means what are these are the zero set of your of that linear part. Correct or not? Correct. Okay. Linear algebra. Linear algebra, right? So what's linear algebra? Or let's say how many solutions to this linear equation? What do you do? You got a bunch of equations need to satisfy. You want to solve for the zero set. Solve for the zero set. How many equations? How many solutions? How to decide? Huh? Got three cases, huh? Infinite, 1 point, or nothing. But how do you calculate? Free variable, very good. Free variable. But free variable has relation with what? Huh? Yes. Rank of the matrix. Rank of, rank of the matrix. So number of dimension of free variable or dimension of this null space and the rank. What's the relation? What's the relation? Rank theorem. Rank plus dimension of null space is n. Okay, so this one is the solution, dimension of the null space. This is the whole space. So you need to take away the matrix. What's the matrix here? Rank of the matrix. This matrix here is just the partial gi over partial x. Okay, okay, make sense? Okay. Okay. So what are we proving? Forgot. Okay, so far we reach here already. Okay, good. Okay, so if P stay inside XRV, what does it mean here by definition? By definition, this dimension of dPV must be greater or equals to R. Okay, so this will give us that rank of this matrix built up by this partial or the linear part of GI to be less than or equals to n minus R. Okay, but another linear algebra problem, you got to make sure the rank of this matrix is less than or equal to some number, then this is true if and only if all the n minus r n minus r minus 1 couldn't be plus 1, right? Let me think. Plus 1 or minus 1? All the minor have to vanish. So minus 1 or plus 1? Last time we used this result, right? Plus 1 or minus 1? Don't know. If you want to make sure your rank, okay, of a matrix less than some number, there's some relation with the minor. What do you think the relation should be? Maybe think of some examples. Let's say 3 by 2. Okay, let's see. If you want to make sure that the matrix have rank 1, let's say, what does it need to satisfy? Huh? What? Same length? Same line? What do you mean? Row in the same line. I want to relate to minor. Do you know what a minor is? Don't know? Don't know what's a minor, man? What's a minor? Joel, how do you cut? Yeah, cut. Take out one row, take out one column, right? Then depend on which minor you want to take. Okay, so what do you need to satisfy? Okay, before that, so let's say this is rank one. Can you look at all the minor? What happened? Ah, length at most one. What do you mean by length?
Rank.
Oh, rank. Okay, rank. Sorry, I didn't hear you. Yeah, rank at most one. Eh, minor. Does minor come with determinant? If it's square, how? Where did we use that result last time? We use it in the detrimental variety. Let's go back to that. Let's see how we use it. Oh, that thing. Let's go. Oh, plus one. M plus one minor vanishes. The rank of the matrix A is at most M if all is M plus one times M plus one minus vanishes. So it's really plus one. Let me think. So how to think about this? So let's check if because in my mind I thought minor come with determinant. Let's check. Let's check. Okay, the minor of an element in the matrix is the determinant of the smaller square generated. Yeah. So actually it's the determinant. I think the one that Joel mentioned is called cofactor. Cofactor equivalent to minor or okay, makes sense. Okay, good. 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 Okay. So does it make sense? Is it immediate or not? Is it immediate to see? No. So can we see some examples? Let me think. Okay, so if you are at rank and most M means what? Means that you are equal equivalence to a matrix with M. What do you call that thing? Pivot, correct? Okay, yeah, M pivot. Okay, so is it easier to see determinant on this reduced row echelon form? Huh? You mean the determinant of that reduced row is 0. Okay, but the claim here is the O m plus 1, m plus 1 minus vanish, right? So after you plus 1, right, you will always include a 0 row. Huh? Uh-huh. No. So, okay, so you start with a rank M matrix. Okay, you should be able to row reduce to a matrix with M pivot, right? So you have M pivot row. Okay, but now you look at M plus 1 minor. So that M have a pivot, right? So you plus another row or another column. So I guess you will always need to add in an extra 0 row. Then that determinant will be immediate that is 0, right? Okay. But you need to show the other direction for this. Okay. At least uh, there's something for you to think about. Why, right? Can understand what? Understand what I said? Okay. But yeah. But actually it's 2 directions, so you need to write it down. Okay. Yes. Does this work for non-square matrix? Let me think. Does this work for, I think, yes. So does it work for non-square matrix? You should be minus is on non-square. Oh, you need to look for a square minor, I think.
My guess is that you probably first do some sort of row reduction in the matrix so that you actually get something like a bunch of zeros. Then look at the square. Like in some sense, like in this case, I will look at the 2 by 2. And then go from there. But yes, I don't think it will work for rectangular matrices.
Yeah, let me see. This statement didn't control whether. Oh, this statement actually got. This is a square.
It has to be.
Yeah. Might not be non-square, yeah. So this statement does it hold for square matrix or in general? Let me think. So let's say this case, right? We have 2 of square. So is this rank that then equal to 1? What's the minus?
Wait, but is this matrix not always a square matrix?
This matrix always a square, let me think.
It's like this is like complete right? Yeah, that should be square.
Because the number of GI might not be equal to 9. But let me see what's the statement here. So let me write down the claim first. So at least we agree with this plus 1. So n minus r plus 1 times minor here of this matrix must vanish. Okay. So if it's non-square, right? Can we do it here? Or not? Yes. Yeah, so this is the point. So the point here is you just look for 2 by 2. Okay, so in this case, let's say this rank is less than or equal to 1, right? So if you check 2 by 2 minor here, the determinant should be 0. For example, you look at this one. 2 by 2 minor. So this is a 3 by 2 matrix, right? So you look at the 2 by 2 minor, it's like you find a 2 by 2 matrix inside here by just removing row of column. For all 2 by 2. For all, all such minors should vanish. All.
That means you look at all matrices, all square matrices of this size, and you get all of each of all the minus of each of them.
All the minors of each of them. All their determinant.
There are different ways to find 2 by 2 matrices.
Mm-hmm. So what are the
So you
different?
have to look at each of them and look at all the minus of each of them as well.
I don't get what you said.
We give here the definition.
Yeah,
The
say.
definition of a minor of a non-square matrix is just the reduce m minus k row and the n minus k column.
Yeah. So that's what we did just now. You just remove row or column such that you get the square matrix. Yeah. Okay.
There are more than one way to get.
Just now I showed you 3 ways. Is it what you want?
Yeah, so for every case you have to do.
Yes.
Yeah.
Yes. So in this case, got 3, right? Three kind of minors, right? 2 by 2 minors. So all of them have determinant 0. Okay. Makes sense? Any more questions? Okay, but obviously this requires proof. This is a linear algebra proof, but anyway. So since we got this minor to be 0, but we always know that the determinant of a matrix is always a polynomial. Okay, so this defines the closed set. Okay, since these are polynomial function, it follows that SRV is closed. Huh? Okay. Okay, any question? Any question? Okay. If you like, try and write this down. This is a linear algebra proof. Okay, so next part is let V be an R5 variety again. Then actually there exists an open dense subset V naught in V such that dimension of dpv equals to dimension of V. Okay, for all P in this V naught. Okay, so this theorem tells you that actually most of the points have this property. Most of them. Okay, it's open and dense. Most of them is satisfying dimension of. Okay, so how are we going to prove this? So we're going to use the proposition we had just now. So let's look at the S of dimension of V. Okay, on V. Okay, so what's this number here? What do you think? What is SRV here? All the points such that dimension of the tangent space is greater or equals to that number. If you put ding V here, what is ding V? How we define ding V just now? It's the minimum, right? Minimum of all these numbers, right? So you have the minimum to everything else, right? So you should get everything, okay? Because every point got a number, right? Okay, so we have this. And next thing is, how about I look at the ding V plus 1 of V? add one more to it. Huh? Not V? Why? Everything. If okay. So if type okay. So if this is V, then yeah, that's right. That's right. That's right. Everyone got what he said or not? If there's if this equal to D as well, if this equal to V, then the minimum of dimension, what's the minimal dimension of tangent space you can get? Everyone else is dimension V plus 1. Definitely you must start with dimension V plus 1. Okay, no. Otherwise, contradict the minimality. Okay. Okay, so we got this two line here. So since S of ding V plus 1 is closed, okay, then actually the open set we're interested is V naught take away S ding V plus 1. Okay, which is open and non-empty. Okay, why is it dense? Why is it dense? You must always remember why is it dense. A lot of argument follow with this similar argument here. You got open here. You got irreducibility. Okay, open set in an irreducible space is dense. Okay, it's a topological property. Okay, if you open in an irreducible. Otherwise, you will produce proper open set such that you can reduce your space. Otherwise, contradict the irreducibility of it. Okay, so open in irreducible set is not empty. Yeah. Okay. How about? Okay. Let me edit it. Open. Okay. Okay. Let's do a bit more. Let's finish up until we reach algebraic part. Okay. Let's go a bit further. So from here, what we'll define here is so for any fine variety F. So if we take the point P in V, we say that it's smooth or regular if the dimension of TPV equals to dimension of V. Okay, otherwise it is singular. Okay. So far, okay. The dimension of V has to equals to dimension of TP. So still can recall how we define the dimension of how to define a smooth point at or hypersurface. It's not using dimension. Still remember? something about the partial derivative. As long as there's one partial derivative evaluated at that point is non-zero. But how many f you are looking at there? Only one f, right? So only one partial derivative equation you are looking at, right? But one of the coefficient is non-zero means what? That is a rank 1. Is rank 1. Okay. Make sense? Okay, so let me put a remark here. So actually this is a generalization for the case of hypersurface. B, okay, which is zero set of f. Since if we can find some of the partial derivative to be non-zero, this just means that the matrix built up by this partial derivative is 1. Okay. So what's the dimension here? What's the dimension of a hypersurface? Which is equals to the mean of dimension of TPV, okay, which is equals to n. Okay, if your V is smooth. Okay, n minus the rank of this matrix here. Okay, and then we'll define something called co-dimension. Okay, maybe not very useful for the moment. If we're gonna make connection to algebra later, maybe it's useful. So we define what it means by the co-dimension of an affine variety. The A and K. So co-dim V here is defined to be n minus dim V. Okay, basically you are compute the rank of that matrix built up by this partial derivative. Okay, two more pieces before we take a break. So one pieces is, so now we define for irreducible affine algebraic set, right? How about general one? Okay, for affine algebraic set. What do you reckon? What's the relation between algebraic set and affine variety? What's the relation? What's the relation? One is reducible, one is irreducible, right? Reducible means what? Huh? Why are we interested in irreducible? We can write them as a, we can write these any affine algebraic set as a decomposition of affine variety. Okay, I can decompose them into irreducible component. Okay, let's say V equal to V1 union of VL here. Okay, so now we want to say, hey, how about points in here that are smooth? How to discuss that? Just now we only know how to discuss on affine variety. So now, how to talk about smooth curve? One thing you need to bear in mind here is we didn't require this VI to have disjoint intersection, right? Okay, one of the points of E could live in quite a few here. So there's a quite strict condition here. A point P in V is a smooth or similarly regular point or V in V, okay, if this P only lies on exactly one irreducible component Vi, okay, and obviously P has to be smooth there, okay, make sense? Okay, sorry. Exactly, sorry. Yeah, exactly one. Thank you. Okay. How about dimension? How about dimension? How do we define dimension just now? Minimum of all the tangent space. Okay. But here, you got multiple VI, multiple minimum. What can you do out of this minimum? Minimum again. Okay, but it's the other way around. So you take the maximum. Okay, so actually the dimension of V is defined to be the maximum of the dimension of the X. Okay, so far okay or not? Okay, so for this week, what we have done, we do an example of blow-up. Yeah, I define a dimension of hypersurface for you, and then I define a dimension for affine algebraic set. Okay, in general. So next week, we're gonna do algebraic characterization of dimension of a variety. Okay, so we will try to compute dimension. Huh? Sorry. What? So we will try to relate dimension of rings to a dimension to on the variety. Okay. And then after that, I believe after those chunk, then last bit of this singularity will do resolution. Yeah, and then after resolution, we most probably will leave this chapter, and then we will go into hopefully devising. Okay. Okay. Any question? Yes.
P is P lies in two or more VIs, but
Mhm.
it does not cross, so you can still define a tangent plane, so it can still be smooth.
So what? So you say, let me draw what you say. You say something like this. Something like this. And then you say this is a affine. Okay. Mm-hmm. Mm-hmm.
So define the tangent plane at that place. So
Mm-hmm.
usually when you say that a point is not smooth, there are usually like self-intersecting, so therefore there is no partial derivative.
Okay. Mm-hmm. You mean, is it possible to define a tangent space here?
Yeah.
So this are two different affine algebraic set or from wait, so I think two affine algebraic set doesn't make sense, right? I mean, you just look at one of them. You are saying that this
You probably won't say
union
I mean, those are
union.
components.
Mm-hmm. I think inside or not. Okay, we will take a break here. We can still think about it because I don't want to eat my time. Okay, let's wait until 5:10. What's the why why you want to think about this?
Because it's, in when we have multiple irreducible algebraic varieties.
But these are affine varieties.
Yeah, these are affine varieties. Normally, then when they coincide at the point, you cannot define the tangent plane here. So therefore, this point would be regular. Oh, this point will be what is the opposite?
Well, I think maybe let me rephrase it. Like you can define the tangent plane for one guy, and then tangent plane for the other guy, and then the intersection would be
Yeah, the intersection, there will be a problem in the intersection because you cannot define the
tangent space.
Yeah, well, where is it? Where is it?
Where's
The last slide. Yeah.
Yeah. So if you want, so think about this example, right? So here the tangent space will have dimension 1,
Yeah, and here is another
then
dimension
1. So the intersection will have dimension
2 or more. Depends on
wait, wouldn't the dimension go down?
Yeah.
No.
the dimension of the tangent plane. Doesn't it?
But it's because he was taking the. I mean, it depends on her.
Where's the
definition.
intersection?
If you take the intersection, then it should go down, right? I mean,
Yeah.
if you're intersecting two, if you're taking two intersection of two one-dimensional things, you should get something which is less than or equal to 1. Think about intersection of two lines, right? The line.
Oh yeah.
So that dimension should go down. It shouldn't go up. If it goes up, then something is weird.
Okay.
Mhm.
Okay, so
So in his example that he drew just now, then somehow the dimension doesn't change. So it will be like a one-dimensional line intersecting with another one-dimensional line.
I think I asked the wrong thing. Okay.
这个奇怪的问题。
So this is algebraic set
Yeah,
有一个 VE not intersection by union.
They're
union.
union. Yeah. Yes.
So normal then you say that if P lies in two VIs, it was not smooth, it was irregular.
We didn't say that. We didn't say that. We just say something is what's the thing that's
It is smooth when it is exactly on one. Therefore, it means that if it is intersection, it is not smooth. Or are there cases where intersection?
yeah, well, I didn't define singular point for general affine set. Otherwise, is it just otherwise?
So somehow you're saying that because in his definition, as long as it lies in two, then it will be no longer smooth.
Yeah,
that's your main complaint, right?
That is quite understandable. So, like, if this line is variety 1 and this line is variety 2, it is quite understandable that at this point you cannot draw a tangent line on it. But so what if that there are like two varieties that actually
That's somehow coincide, right? I understand.
Same point, then technically you can still define a tangent line here, but according to this definition,
then it somehow is not smooth. Yeah.
So
which is not ideal, but
I think this
no
case
pun intended.
cannot happen. I think if you agree on like seemingly open set,
No, even if you agree on a point.
wait.
No, even if you agree on a point.
or tangentially met.
Yeah. I mean, this is easy to construct, right?
Oh yeah.
This one, this
yeah.
one I think is
Infinite points, which therefore
everything.
Yeah. This one doesn't happen, but this one definitely happens.
So
Then I agree that it seems like you should still be able to define a tangent, but you would still like to call this space not smooth. And I think that is the general acceptance. I think so, yeah. You would still call this space not smooth somehow.
but I didn't have the singular point.
Yeah, like it seems weird, like because maybe you would like to agree. We would like to say that this guy has like exactly. We can have like, but no, that's somehow not the general definition.
Okay.
I think the idea is somehow like when you reach this point, there's technically two directions that you can move. Right? So although it looks like you can define a tangent line, but not quite. Like it's because
if you use integration, you
Yeah,
cannot
yeah,
integrate.
yeah. Somehow like it's not really a smooth point anymore. Like once you go there, you almost hit like a train track, and then it's like, okay, well, which way do I go now? It's no longer. But it's a good question. In fact, the resolution of things like this would look exactly like this, but slightly separated. If I really wanted to resolve whatever that means, at some point you will learn resolving singularities. It will be exactly doing things like this, which looks like that.
So like the blow up
Yeah.
like the blow up, it makes this graph
Yep.
into like this goes from above and then this goes.
Yes. 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 So for this guy, it will make it into something like this. It will slowly separate it in some way. Yeah. Depending, this
Yeah,
is very picturistic, but but the idea is something similar.
I think the picture is so well. Okay, you want to use the blow up thing to talk about it, right? So so this one and this one is on the same page. Because you see, if it is really symmetric, so these two dots should be on the same height. Okay, it's the same height. So one will go down,
At the point they still have the same tangent, so they still coincide at the same points using the blow up that we learned.
So yeah, so yes.
So this technically still did not solve the whole problem. We might have a different kind of blow up for this one.
Let me think. So in solving, so only this point I don't know what happened, right? Oh, so this is the negative. This one will go positive, right? Go down and this go up. It's the same height, but this one is at the opposite side. And then
Or just something like this.
yeah. Not that right. It's not that. Actually, it's not that right because this one is an infinity point. So how do you approach here? Your line will go like infinity case there. Actually, it's split out. Can split it out, right? Because you are going from negative
To infinity, and you make this go on. But this is the same lines, right?
same line, yes.
So
Both have to go to infinity.
so they still meet at infinity.
Okay, let's say we very artificial. I don't know is it algebraic or not. Right, Lisa? I feel like not algebraic.
What
It's algebraic.
of the
Okay,
one that we
use-
draw? Of course, I take x square equals. Just do x y equals x square and then do negative. No, this is of course an algebraic set that you just take. It's literally y. It's literally like y equals x square and then y equals negative x square. It must be. They meet at the origin. I think the blow up of this thing will be slightly weird. Like it will. I have a feeling that on the blow up picture it will actually separate two things. I think so. I wouldn't be surprised if on the blow up picture you actually somehow separate two things.
Is there something like a Desmos or online blow up?
No, I'm not a blow up guy, so I don't know. I don't know.
But at this point, the tangent.
Their tangent means their tangent is the same.
Yeah.
point.
Yeah, that's an point.
So if I remember that the height or the value of the value of the projective space
Is a tangent.
determined by the tangent.
Tangent.
So if the both of the line reach the same tangent on the
Then they'll
origin,
make the
then
same
they will
height, right?
reach the same height.
Same height.
Yeah.
Same height and same point. So
Unless we use a different kind of
Yeah, it
blow
might
up,
be different. But yeah,
I don't know if that
I
is
don't
a
know if that
different kind of-
construction actually gives you the proper blow up, right? I mean, the blow up satisfies some abstract property, and the constructor that he gave you for this particular example is one way of constructing the blow up. So I think this one you require something that's slightly different. The property should still be the same, but the construction should be different. That's my guess.
So I can separate.
Yeah, maybe you need to blow a few times. Maybe you need to blow a few.
You can blow a few times.
Yeah. Sometimes, yeah, we
So I think because the first time you blow it up, it will probably intersect now nicely this way, and then you do it again.
Then you will separate.
Yeah, and then you
Okay, I can at least imagine the first time, but I don't.
yeah, I don't know what the hell's gonna happen. Yeah. By the way, so in your definition of dimension, in this two line example,
okay.
so the dimension of this guy is 0, not 1.
Why 0, not 1? How do you work it out? Dimension of the
Also, the
origin.
dimension of V is the maximum of all the VIs. 然后这个呢，这个 example 呢
啊，这个什么啊？
，dimension 是0。
谁的 dimension？那个点哦，那个 D 本身
V 啊
，D 本身不可能哦，因为
因为
来
minimum 哦，刚才所以我才 confuse，
哦，
对吗？你看你上去看一下，
那个会不会不是 irreducible？
能吧？y square 多。好，那个是一个
这个是吗 ？dimension of P。
对，因为 dimension of V 是 minimum of all the points 哦，我以为是 maximum 呢，but 那我有。
你讲那个中间那个点是 dimension 0是吗？
哎，我的兄，因为 I mean intersection of 对吗？
那个是 singularity，
对，那个 singularity 嘛，所以它这边
singular
这边是 e，这边是 e 嘛，所以它应该是变0。
那个 singular point 的话，不是那个 singular 的。
对，因为你看啊，我 tangent p of 那个 point 就是 intersect of 两个 tangent line 啊，对不对？
但是
就是这个，
没有，你那个是 hypersurface 啊，就一个 f 罢了，
对啊，
你就一个 f 罢了，
对啊，只有一个 f 啊，我知道啊。
你就一个 f 罢了。然后如果你是在那个 singular point 的话，其实那个 dimension 是跟那个它整个 space 是一样的，更大，那个点的 dimension 更大，因为你想想看嘛，那个点有2个方向嘛，但是其他点你只有一个方向
哦
啊。OK， 差不多要 start， 你还要用这个吗 ？OK， 等一下给我讲完。
我可以试这个啊，
哦，你可以用这个，只是 like 我这里跟你说一下，给我讲完这个我再给你。OK， 还是你要讲？你讲。OK， Hello，let's start. Okay. So, while I discussed with Edmund this morning about blow up, we found a very good model here. Can you recognize this as a blow up? Recognize this as a blow up? Okay. So you can you imagine we have a A2, right? And then we have lines through the origin, right? So it's like this, and then you slice through using a line through the origin, and then you plot it up. Every line have gradients, right? So the gradient is the height of this line. So you can see that the middle straight line here, this full scan here, got the pre-mesh of the 0, right? Yes, I haven't traced it yet. So if you notice, there's a middle line here is the sectional divisor. Okay, but yeah, it is twisted. Why? Because got gradient, right? Okay, so it's twisted. Right or not? But note that P1 is an A1 with an infinity, right? Meaning what? Top infinity and bottom infinity is the same. You join them together, or you twist. Eh? Yes. Actually, it's a Mobius
That Mobius square.
topologically. Okay. Who wants this?
Of course, you can construct this at home yourself, right?
Well, you can play around with this. Okay. So give the time to Evan. You have to present or want to like a podcast or what?
I don't know. I mean, I prepared something, so we can talk about some stuff. But
Yeah.
I mean, I'm not your lecturer. I don't care whether what kind of marks you get. So we can be slightly more informal and we can go for that.
You accept questions from them.
Oh yeah, of course. I mean, like why
Just ask any bizarre question.
yeah. Feel free to ask any question. I mean, like the rule in mathematics is always that there's never any stupid question. I mean, we all start somewhere and we all ask stupid questions at one point of our life. So there's never actually any stupid questions. Okay. Is it possible if I just put it somewhere so I don't need to hold it?
Oh.
Can
you use it, mic or not?
I can use this. I mean,
This one.
if this one works.
I think should work.
Okay. Test. Yeah, I think that kind of works. You all can hear me, right? I'm pretty loud, so I think it's going to be okay. Okay, so Keesing asked me to present something in algebraic geometry which is related to my research, which is pretty hard because I'm technically not an algebraic geometer. The last time I did algebraic geometry was, well, how many years ago now? 2017. So that's 8 years ago now, and I haven't touched algebraic geometry since then. But it's definitely no doubt that like algebraic geometry is very important. Like it allows it's like I care more about topology in some sense, but every time when you have something that is also realizable as algebraic geometry, it gives you slightly more structure. Like you have actually geometry in it rather than just topology, which is just like open sets, closed sets, which is a lot of things, right? As you can see. So what I'm going to do is somehow like just try and present to you what I do for research. I study a lot of something called quivers, which I'll introduce very shortly. And then I'll show you how like algebraic geometry actually allows you to prove certain things. Kind of cool, right? I mean, like somehow we started off with something that's completely algebraic. And then at some point in your life, you realize that, well, actually, like to prove certain things, you need some algebraic geometry to come with it. Okay? All right. So any questions before I begin? Oh, yeah. Also, I guess Keesing asked me to talk a little bit about my life, but I don't really know where to start. I mean, I'm from Malaysia. I come from Penang. I did my undergraduate and PhD both at the same university as Keesing. So I spent about 9 years in Canberra. And yeah, after that, I did a postdoc in Paris for 2.5 years, which was quite fun. I learned some French. Not that I'm perfectly great in French yet, but I learned some French. And then now I'm back in University of Sydney again. So I'm back in Australia again. But I'm still a postdoc. So. Okay. All right. So let me begin with definition first. So first, I should tell you that my talk will definitely not be like Keesing's in the sense like it will probably be closer to research talk than a lecture. But if you're confused about anything, feel free to ask. Okay. So let me start off with the definition. So everyone knows what a graph is, right? Hopefully you've taken. I was told that you learn discrete math, and then at some point you know what a graph is. Okay. So if you forget what a graph is, just remember that they're just points and some lines joining them. Okay. So for me, a quiver is an oriented graph, and that's it. Okay, so basically think of it as like for a graph, you just have points and then lines connecting them. Now I have arrows connecting them instead. Okay, so just some examples. You have maybe 2 points, 1 arrow. Okay, right, so that's a graph, which is just 2 vertex and 1 edge, and then now I've oriented it from the left to the right, and that's it. Okay, and then you can also do, I don't need to assume that my arrow between 2 vertex, there's only 1 edge. I can do something like this as well. And even if you want to be fancy, you're also allowed to do something like this, going in different directions. Okay, all those things are fine. And of course, you can have more than 1 vertices, so maybe something like this. Okay, so these are all just quivers. Okay, if you're interested in the reason why quiver, I believe quiver came from the word. You know how archers has like this bag that they put that they have on their back, and then they put arrows in it. That thing is called a quiver. So hence the name. Okay. So a collection of arrows is what a quiver, what a quiver means. Okay. So let me now then say that what I care about. So I'm a representation theorist. So I study representation a lot of things. And here now I'm just going to give you a definition of what it means to represent a quiver. Okay, so if you have taken, maybe most of you have this representation theory before, but the point is to take a mathematical object and then study it in terms of matrices, because matrices is essentially all we know about algebras. Like tons of things, even AI nowadays, if you're more hype into those kind of things, like they're all built on matrices. They're all built on linear algebra. So we'll do something similar here for quivers. And so I'm going to give you a definition of what a representation of a quiver means. So actually, maybe before that, let me come up with some notation so that everything will make slightly more sense later on. So my set of vertices, I'll denote by Q0. So this is the set of all vertices. Okay, so all the dots. And then Q1 will be all of my arrows. Okay, so this is the set of arrows. Okay, this is just notation. All right, so given a quiver, maybe I'll write it this way. So given a quiver Q, Q0 will be the set of vertices, Q1 will be all my arrows. Okay, so a representation of a quiver Q consists of the following. So for each X, a vertex, I want to assign, so let me do Vx, a vector space. So for you guys, it's probably good enough to really just think of this as like Cm for some m. Okay, so just some vector space of any dimension. All right, the m there is arbitrary. All right, you can do any dimension. And then, so this is what you'll do on the vertices. And then on the arrows, you attach linear maps. Okay, linear transformations. So for all arrows, which I'll call A, that goes from X to Y. Okay, so these are arrows. So this is an element in Q1. I will attach a map, which I'll call VA, that goes from VX to VY. Okay, and that's it. All right, so you've taken a quiver, which is just dots and arrows, and then now to every vertex, I've attached Cm and Cn, and then to every arrow, I put on a matrix. Okay, so let's look at some examples. And again, generally, I'll always use V to denote my representation. So representation V consists of a bunch of data with respect to X, which are my vertices, and a bunch of data with respect to my arrows A's. Okay. So let's see. So for example, let's say that my quiver is this guy. All right. Then what is the representation? Well, I can take C, and then let me just use the identity map here. I'll just times 1 if you want. All right. Then of course I can also do maybe C square, C here, and then now my map between C squared to C, what should it look like? What kind of matrices does it look like? It should look like something like a 2 by 1 matrix, right? So maybe I can chuck in like 1 and 3 or something like that. All right, you happy? So is this like a 2 by 1 matrix? Because, sorry, 1 by 2, depending on how we say things, but something that looks like a row. Okay, and all these things are representations of my quiver. Okay, so in mathematics, we always ask ourselves, what do we mean by two things being equal? Right? Whether or not me and Keesing are equal, well, depends on whether you think of that. Okay, we're equal in the sense that we're both human beings. Okay, we're not equal because he's a lecturer and I'm not, something like that. Right? So we have to agree on what we mean by equal, and then we'll go from there. Right? So let me tell you what it means for two representations to be equal. Okay, and we use the word isomorphic, like in many mathematical words. So let's say that so let V and W be two representations of my quiver Q. We say that V and W, or we say that V is isomorphic to W. So that is V is isomorphic to W if the following data holds. So if there exists a bunch of maps, or maybe let me write it in a more formal way, for all X in X. So again, for each vertex, there exists some map. I don't want I want X. But we have a map Fx, which goes from Vx to Wx. Okay, so we try to relate the two vertices that we have, such that two things hold. The first thing is that fx is an isomorphism. And here, what do I mean by isomorphism? Well, I'm giving you a map between two vector spaces. And when I say isomorphism between two vector spaces, I just mean a linear map between two vector spaces which are invertible. Okay. In particular, more concretely, I have a matrix and I want my matrix to be invertible. Okay. So for each of my vertex, I want that to hold. And for the other thing, then what I want that for all arrows x to y, I want the following diagram to commute, which I'll explain what I mean very quickly. Okay, so what I mean by this is a commutative diagram. It means that if I first take this matrix here, okay, and then I take this matrix here, it's equal as morphisms as this matrix composed with this matrix. Okay, that's it. So this is just a diagrammatic way of representing what we mean by commutative. But all I mean is just that if I take, so more precisely, what I'm saying is that, so this map is VA, this map is WA. So all I'm saying is that if I first do VA and then do FY, it's the same thing as if I first do FX and then do WA. Okay. So, but remember that suppose we know that our maps are invertible, right? So fx here is always an isomorphism, right? So if you want, this is equivalent to saying that if I take VA, or maybe, sorry, let me maybe do the WA version. If I do WA, and I don't know what WA is equal to, well, it should be equal to FY composed with FA composed with FX inverted. Okay, are we happy? All right, so this is what we mean by two representations being isomorphic. All right, so let me then ask you the following question. If two representations are isomorphic, what do we know about the dimension of the vector space on each of the vertex? Right? What do you know about the dimension? So for example, you know, like V is a representation, V is a representation, W is a representation. On each vertex, I have Vx for V, and on each vertex, I have Wx for V. For W. And I want this map to be invertible. So what does that say about the dimension of Vx and dimension of Wx? It's the same dimension, right? So in particular, like whatever this vector space is and whatever this vector space is, if I represent them as matrices, they have to be a square matrix and then invertible, right? We were just discussing about square matrices being square and not square. If it's not square, there's no hope of talking about invertibility, right? So this must be an invertible matrix, therefore it must be the same dimension. Okay. So with that, then the only way that I can ask for two things to be isomorphic means that at the very minimum, they have to have the same dimension at each vertex. Okay, and I'll write down a notation to remember this piece of data. Okay, so this is now the next definition. So the dimension vector of a representation V is given by the vector that looks like alpha V, which I'll define as dim Vx, and my vectors go through all of my vertices. Okay, so if you really want to write it down as a vector, put some ordering in your vertices, or put some number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then write it down as a column. Otherwise, this is just my notation. Okay. All right. And in particular, maybe more precisely, I want to swap my notation a little bit. I would like to think of this as like a function from my vertex set into natural numbers. Okay, and what I mean by this is that alpha for each vertex x, it is exactly given by dim, alpha v of x, this is exactly given by dim vx. Okay, so this is just notation. I'm just swapping between thinking about vectors and thinking about functions from a point to something else. Okay. So now let's think about the space of all representation. So now consider, so let me do it this way. So let alpha be just some function, right? Just some function that goes from Q0 to n. Okay, so this is just the dimension vector. Okay, so just a collection of numbers that tells me what dimensions I can only put on my vertices. All right. Then I can look at the following set. I'm calling it a set for now. So this is the set of all representation with, so let me do it this way, all representation V with alpha V equals alpha. Does this make sense? Okay, so I'm just fixing some dimension vector. So I'm telling you what numbers, what dimensions I can put for each vertex, and I'm looking at all possible representations. Okay, so this is maybe slightly confusing for now, but let's look at some examples, all right? Again, let's do this example first, all right? And let's say that alpha, and when I denote by alpha, all I'm going to do is that I'm going to tell you, or maybe let me just give them names. So let me call this x, y, and let me call this arrow A, right? In the simplest case. So let's say that alpha x is equal to 1, alpha y is equal to 1. Okay, so what can my representation look like? It will always look like C, C, okay? And then here, this part here, I just have to attach some matrix. But what are the possible choices? All linear maps are possible, right? But what are the linear maps between C and C? C itself will be C itself. So this guy here, I can literally put any number, what's a good name for a number? K, where K is an element in C. Okay, so if you want, this is all. So if you want the rep 1 of my query over Q is exactly just given by K in C. Or if you want, it's the same thing as thinking of it as just all complex numbers. Okay, so now let's go one dimension up. What if now alpha x equals 2, alpha y equals 1? Right, then now everything looks like C squared to C. And what are the possible choices here? What kind of elements can I put there? What are all the linear transformations from C squared to C? 1 by 2 matrices. Okay, so again, rep of Q1, my query over Q, it's really just all 1 by 2 matrices with entries in C. Okay, and now you've learned some algebraic geometry. If I call this an affine variety, will you be happy? I mean, it's okay. It looks kind of weird, right? But because what's the point? I mean, the whole point is that matrices. I'm not asking anything about my matrix yet. I'm just asking it to be a 2 by 1 matrix. So this is just a collection of 2 by 1 numbers in C. So of course it's a affine variety because, well, it is affine 2 here, right? This is just A2. Okay. All right. So more generally, so here's maybe an exercise if you want to try and do something interesting. So given rep alpha of a vector of a quiver Q, this is just the same thing as taking all possible matrices from, let me think, alpha x, alpha y, C. And I'm taking the product over all possible arrows that shows up. Okay, so maybe because previously we didn't see any product here, so maybe let me do one more example. Let me say that Q is now equal to 2 arrows. Okay, X, Y here, and maybe A here, and then B here. Okay, then this guy, so rep of maybe let me do 2, 1 of Q must then be equal to matrices of 1 by 2 C times, right? Because one of them, so one of this guy should be this, and the other one should be this. So I need two copies, hence a product, a tuple, a pair if you want. Okay.
So one of them for A and another one for B. That's just notation. Okay, are we happy? Right, because for every arrow I have to give you a map, right? So if I have 2 arrows, then I have to give you 2 maps. Hence, this guy here, 1 for each map. Sorry, 1 for each arrow, 1 map for each arrow. Okay, and again, it's an affine variety. It's just a product of affine varieties. Okay, but what do I mean by 2 things being the same representation, right? So maybe let me go back up to my picture here, right? If I start off with this representation itself, just start off with V itself, I can always just compose it with any invertible, so matrix here, and compose it with any invertible matrix here. And then I'll get a new representation, which we call W. Okay, so let me rephrase that. So
In that exercise, the Q only have 2 vertices, or
no.
Yeah.
No. So this exercise here, Q is general, and the product here is exactly going through all possible errors. Okay, so that's what the product that sign means. So product A from X to Y means I do it over all possible errors. Okay, so the number of arrows decides the number of copies of matrices that you want. Okay. Potentially of different sizes as well, right? Because if you have more vertices, then you have potentially different sizes for different errors. Okay. So if you're given a representation V, let's say V is some representation with dimension vector alpha, right? I can always do the following, right? I can start off with Vx to Vy, right? And I can transform it as far as I'm happy to, because I can do something like first do this. Maybe let me do it this way. Vx, Vy. I can construct this new map here by just saying that, okay, take any invertible matrix that I want, which I'll call Fx. Right? And then take any invertible matrix that I want here as well, which I'll call F inverse Y. Okay. This composition here, first do Fx and then do V alpha and Va and then do V inverse Y, gives me exactly this map here. And that constructs me a new matrix. Okay. So what does this mean? So let me give you the following general definition. So again, alpha is a dimension vector. Then I'm going to denote the following product group, which is just GL of alpha. And all this does is just giving me all of the invertible matrices on each vertex. Okay. So over all possible vertices, I'm taking the invertible matrix of size alpha x, right? So of size equal to the dimension on set on my vertex x, and look at all the invertible matrices C, right? Can you see the following claim? G alpha, first of all, is a group. Are we happy? Right? G alpha, each piece here is a group, right? A product, and by a product, I just mean a product group. That's it. Okay, so they multiply component by component wise, is the picture. Okay, my claim is that G alpha acts on rep alpha Q. Okay, how does it act? Given an element in here, what does it look like? It looks like a bunch of invertible map for each vertex Q naught. Okay, and if you go back to the picture that we had just now, this one right here, interesting. I do not know what it's going to copy, but let's hope that it doesn't copy. Okay, magic. This is how it acts, right? I start off with some representation which has this as my vector space in vertex x, this as my vector space in vertex y, and with this map, right? And now all I've done is just I'm going to pre-compose it by this guy and then post-compose it by this guy. And that gives me a new map. So the vector space itself doesn't change, but the maps has changed because this is now a new map. Okay. So now we have an action of a group on a set, which turns out to be an algebraic variety. Okay. And moreover, this is something that you haven't learned yet, but this guy, each of this guy is what we call an algebraic group. Okay. And what we mean by that is that not only that it is a group, it is also an affine variety. Okay. I don't know if you've seen this example before, but if you don't know why this is an affine variety, I urge you to write down the polynomial that defines GL2C. Okay. I'm not asking you to do GLNC because I do not want to do that either, but GL2C is what you should know how to do, okay? Tell me why 2 by 2 matrices, which are invertible, is the zero set of a polynomial. Okay, it's a hypersurface according to what Seng has been defining. Okay, so it's a hypersurface of my hint for you is that it's a hypersurface of that lives in the 5-dimensional affine space, not 4. A priori, it seems like you only need 4 entries, but you have to do some trick to push it up to 5 and then define a polynomial there. Okay, if you try it and then you can't remember, ask Seng. Okay. Okay. All right. So here's my first lemma, which I won't prove, but it should essentially follow from the definition that says that B is isomorphic to W if and only if they have the same orbits. Okay, right? So remember when are two representations isomorphic? Well, exactly when we can find all these invertible maps that transform them to each other. So if I now take the orbit under my group action, it basically traces through all of the possible representation that I can get. Right? Start with one and then just pick all the invertible maps from G alpha, so the product of all the invertible matrices, and then just start tracing through. That is exactly what orbit means, right? And then you get all of these representations here.
But isomorphic orbit.
Yeah, for the time being, let's just say bijective as sets, right? If you really want to, which you can really literally write down, right? Somehow, okay? Like it's canonically isomorphic. The strong term is that they're isomorphic as a algebraic variety, but of course, for the time being, just sets, right? I mean, of course, you can believe that they're the same thing as sets. Yeah, in fact, like once you learn more about algebraic group, you can study there's all the things that you know about algebraic geometry is going to come into play about like orbits are close, dimension makes sense, and then you can use dimension to do some counting, which I'll do very, very soon. Okay, are we all happy up to now? So I've told you what quivers are, and then I told you what representations are, and then I told you what they mean to be the same. And now we've understood that, well, for them to be the same, all I have to care about is just that I can start with my representation. What are the things that are the same? Well, as long as I take the orbit, I've covered all the things that are the same. That's it. Okay. So if you want, the slogan here is then that rep alpha Q decomposes into all the possible things which are not isomorphic to each other of GL alpha B. Okay, right? It's just decomposing my space into a bunch of things like this. Right? This is really a slogan. Do not take this as a mathematical statement. Right? But you can technically fix this to make this correct. Again, if you know some algebraic geometry, there's some ways to make this correct. Okay. All right, are we happy now? So a general question about representation theory is the following question, which says that when, let me write this as a question. When does rep alpha Q has only finitely many orbits? Here, right? So all I'm doing is just the following, right? Take one representation, look at all of its orbits, see what's left. Take that, look at its orbit, see what's left, and then repeat this procedure. When can I guarantee that actually by just doing finitely many steps, this procedure actually stops? I've covered all of the possible representation. Okay. And here's the theorem. Which goes one direction. So suppose that for all alpha, so for all of this possible dimension vector Q naught, right? So these are all dimension vectors. Q has only finitely many representations. Okay, so I'm going one way now. I'm assuming that it has finite. What can I say about my quiver? So it turns out I don't know what to say about my quivers yet, but I can write down an invariant for my quiver. And by invariant, all I mean is just that it is something that I count, some number that I assign to my quiver that tells me that if two quivers are the same, if and only if the numbers assigned, not if and only if two quivers are the same, they must be assigned the same number, and that's it. Doesn't go the other way around. Two quivers that are different might be assigned the same number, but if they are the same, they must be assigned the same number. Okay, and the definition goes as follows. So it's going to take alpha, so any possible dimension vector, and it's going to output the following number. I'm going to sum over all possible x in Q naught. Okay, so this is just taking the square of my dimension on each vertex. That's all I'm saying. And I'm going to do minus over all possible arrows of alpha x, alpha y. Okay, so it's just multiplying. So for each vertex, I'm squaring the dimension. For each arrow, I'm multiplying the dimension of two things. Okay, this seems weird for now, but let me just quickly convince you that actually, in fact, this guy is just dimension, as Seng has defined it just now, of GL alpha. Do you agree? Okay, so as a affine variety, right? GL. So don't think about GL alpha yet. Think about just each of its piece. Each of its piece is just GL M of C, right? And that is an affine variety of M by M dimension, right? So 2 by 2 matrices which are invertible have exactly dimension 4, right? Again, if you don't know why, write down the polynomials and then hopefully you'll be able to check what it is. Okay, so this is just dimension of GL alpha. This part here is exactly the dimension of all possible rep Q alpha Q. Right? Remember what is rep alpha Q? It's just matrices of size alpha x times alpha y. So again, this one is easier because this is just affine space of exactly this dimension, right? Because all the entries I take, and that's it. Okay, so as you can see, this whole piece of data here is an invariant of a quiver, right? Because once you give me a quiver, I write down this number, I write down this function, right? Technically, this is first of all, this starts off being a function, right? All that I need to define this function here only depends on my quiver data. Okay, and you can check that if two quivers are the same, they have to return you the same numbers. Okay, so this is what we call a quadratic form, actually associated to a quiver. So given a quiver, I can write down a function that takes in as inputs any dimension vector, and then just outputs this number right here. Okay, and the claim is that if Q has finitely many representation, this is actually always greater than or equal to 1. Okay, so whatever this number is, whatever this function is, if it takes in a dimension vector, and if I know that my quiver has only finitely many representations, this function always has to output numbers greater than or equal to 1. Okay. a priori everything is just integers, right? Because this is some integer. This is also some products of integers, sums of integers. So all this thing here, I just know that it's an integer, potentially negative. But the claim is that if I know that Q has only finitely many representations, it can only output number greater than or equal to 1. A very strong non-negative, in fact, positive assumption. Okay, so what's the proof like? Let's see how much we can do from the proof. Okay. All right. So what do we know about the proof itself? So let's see. So we know that if I try and decompose rep alpha Q, okay, the assumption was that there's only finitely many in isomorphic representations. Okay, so it looks like GL alpha times V1, GL alpha times V2, GL alpha times Vm for some m. Okay, finitely many orbits. And I'm just indexing them from 1 to m. That's it. Right? Finitely many isomorphic representations means exactly this, right? I only have finitely many copies of it. Okay. So here's where algebraic geometry becomes useful. I know that this has some dimension, and I know that each of these pieces have some dimension. Okay. And if you think about it, if I want to try and fill a plane by lines, how many lines do I need? Infinitely many, right? Think about your projective picture, right? I need to turn somehow, like one way to fill it is take this line and just twist over all of them, and that I require infinitely many. Is it possible to ever fill a plane with finitely many lines? No. So here's the lemma again, which I won't prove because I technically don't know how to, but again, algebraic geometry is what tells you that this is true. There exists at least some Vi such that dim of GL Vi is the same as the dimension of rep alpha Q. Okay, so the idea is that if I give you some space of some dimension and I chop it up into finitely many pieces, at least one of its pieces have to have the same dimension, right? So again, think about the plane, right? I mean, I can't fill it up with finitely many lines. I have to have at least some regions which are dimension 2, and then I can fill it up with finitely many pieces. Okay, and that's the lemma. Right? So what this means now then is the following. I have BQ of alpha, which I've told you that is actually the same thing, although I started off writing it up as just something that depends on quiver, is the same thing as dimensional GL alpha minus the dimension of rep alpha Q, right? And this is complicated to study to begin with, right? This starts off as something that is slightly more complicated, but now I can reduce it one step down because this is the same thing as dimension of GL alpha times Vi for some Vi, right? I don't know what it is yet, but for some Vi. Okay. Now I need the second lemma, which I like to think of it as the orbit stabilizer theorem. Hopefully you still remember some sort of orbit stabilizer theorem from your group theory, for finite group theory, right? Again, something similar holds for algebraic geometry. And what do I mean by that? My claim is that my dimension of GL alpha minus my dimension of GL alpha Vi is exactly the same as the dimension of all the fixed points of GL alpha on V. Okay, so this is exactly orbit stabilizer's theorem. So this, sorry, let me be slightly more precise. What I mean by this is that I look at V and I look at all the matrices that fix V. Okay, all the matrices that fix V. Okay, so this is stabilizer, right? This is orbit, this is stabilizer, and I've just done the yoga, which just says that stabilizer plus orbit equals the whole group. Okay, this is a orbit stabilizer theorem for algebraic geometry. Again, I'm not going to prove it, but it's hopefully you can at least trust that this looks reasonable, right? Okay, But now let me convince you that this number right here is in fact greater than or equal to 1. Okay, what I mean by that is that, well, I can at least find something that's one-dimensional that fixes V. Okay, and here it is. So H alpha, let me define them to be exactly all of the matrices, the product of matrices for each vector, for each vertex that looks exactly like just lambda times identity. So this is just my notation for the A alpha x times alpha x identity matrix. Okay, so this is just the identity matrix. And H alpha here is exactly the set of all such elements, such that alpha is just some invertible elements in C. Right? So if you want, all I'm just saying is that I can scale every single vector space. Right? So this is just a bunch of matrices which are just diagonally the same number, and it's non-zero. Okay, it has to live in the invertible matrix set. Okay? Claim. So take this to be this set. H alpha acting on V is exactly equal to V. So if you want, that is H alpha is in GL alpha of V. Right? And the dimension of this guy is definitely more than 1. Okay? And that proves, going back to this picture here, that gives me this is greater than or equal to 1 from this lemma. Okay, and that's it. That's the proof. Okay, so we started off with something that is just on a quiver. For some reason, I pull out of my head that I gave you this function that computes something about my quiver, right? It's a function that takes in dimension vector and then outputs numbers. And I tell you that actually this function is very interesting because it always returns positive numbers if I know something about my quiver being finitely many incomposable representations. So you can actually take this number here, take this function here and do it for all kinds of examples. So the example that I want you to try and do is the following. Take this quiver. Take the quiver that is 1 vertex and 2 arrows. Right? Show that BQ of the vector 1, 1. Okay, so my dimension vector is exactly 1 on the first vertex and 1 on the second vertex as well. Is in fact 0. Okay, so this is not example, this is an exercise. Okay, so this is the first thing that you do. The second thing that I want you to do is show that rep 1, 1 of my quiver Q has P1 many representations. Okay, and let me be slightly more precise. I'm using fancy terms here. I'm telling you there's P1 many of them, but you've all learned projective space by now, so that's fine. But basically, I'm telling you that all of the representations of the dimension vector 1, 1 looks exactly like the following. So on the first vertex and second vertex has to be C, right? Because my dimension vector is 1, 1. On this guy, what can I do here? Well, some number in C, right? Here is also some number in C. So my claim is that if I give you 2 of these, so this representation and this representation, CD, are actually isomorphic representation if and only if I look at their vectors in projective space. Does this notation make sense to you? A, B, C, D in brackets like this? Good. They are the same in P1. Hence, my statement here has P1 many representation. In particular, how many representation does it have? Infinitely many. Okay, are we happy? So, okay, I've basically finished here, but let me say a few things just about this statement right here. So at this point, all I've done is just I've told you that if given a quiver, if I assume that it has finitely many representations, the graph, this function here that assigned to every possible quiver has to have this property. It turns out that you can classify all of this kind of graphs. Okay, and you know what they look like? Well, it turns out if you're one of those guys who are studying Mackay correspondence right now, this is ADE graphs. So here's my second claim. So here's the punchline for those of you who are very interested in doing Mackay correspondence right now. Here, so given Q a quiver, the following are equivalent, P, F, A, E. I'm just being lazy. So the following are equivalent statements. BQ is positive definite. If you don't know what this means, ignore me. But if you know what this is from bilinear forms, then this really just means positive definite. The second thing says that BQ is greater than or equal to 1 on all dimension vectors. Okay, so the condition that I wrote down just now. And finally, it says that Q is of the form ADE. I won't draw all of them right now, but basically what this means is that if I forget orientation, this is a type AN example. 1, 2, 3, 4, and there's a type D example, which basically looks something like this. And then the type E exceptional ones, which I will not draw. In particular, there's only 3 families. Well, in fact, 2 families and 3 exceptional types, which all live in type E. And that's it. Okay. And even better, turns out that the converse is also true. So as long as if you know that your quiver is of this type, you know that there's only finitely many representations. Okay. So that's the application. I mean, again, I'm not really an algebraic geometer, but I'm interested in studying matrices. I'm interested in studying quivers. And as you see, matrices are algebraic objects, right? They are affine varieties and so on. So algebraic geometry becomes very useful in studying these kind of things. And this is one application that you will see if you ever, especially if you're ever going into quivers. Okay, so I'll stop here. Thank you.
Before, don't jump. Wait,
Just take it out.
not take out. Oh, I need to off one first. Okay. Okay. Thank you very much. But before we go off, right? Can we have last word from Edmund?
Last word.
No, wait. No. Not your last word for the so last word for these lovely students. Okay. Maybe try and give some encouragement for them, like